Hey, what's up? It's your old pal, Mr. Cook, and we're going to go through the Unit 6 uh, test review. So we went through the first 6 problems. Now we're going to do, I guess, the next 2. Yeah, we'll do number 7 and number 8. All right, so number 7 says a radioactive sample which contained 50 grams of mass at time t equals 0 decays exponentially. Well, if it decays exponentially, we already know a lot about it. So, for example, if we have to write a differential equation around this, it's going to look something like this. Okay, so like if it's a sample of something, let's just say that amount of mass that it has, we'll call it A. If it decays exponentially, then that means that the rate of change of the amount of mass that we have over time is going to be proportional to the amount of mass that we have. So part A, that's how we write it up. We write up like that. Now we're going to figure out what K is in a little bit. So that's going to change in a little bit. We're going to figure out what that K number is. But the differential equation starts off like this, okay? Next, it says to solve the differential equation, to write the remaining mass as a function of time. Yeah, no problem. So for part B, the solution for this, the general solution, you can just memorize it. If you know it's going to be exponential, then it's going to turn into this. The amount that we have, A, so like that top part, A, that top variable, is going to be equal to some constant times e to the k, that constant, times t, okay? And I know a decaying exponential relationship is going to end up having a negative k. Well, we don't know that yet. We're going to solve for k using some initial conditions. And we have the initial conditions. It says that the radioactive sample, which contained 50 mass at time t equals 0, that means that we have a 0 for t and a 50 for g. That's an initial condition. And then after 75 days, the sample of the mass is down to 30. So at 75 days, it's down to 30 grams. So we're going to use these two initial conditions to solve for these two unknown values, C and K. All right, let's start off with the first initial condition, 0, 50. And this is going to allow us to solve for the differential equation as a function of time. So here we go, ready? 0, 50. So 0 goes in for T, 50 goes in for A. So 50 is equal to C times e to the k times 0. Well, 0 times k is 0. And e to the 0 is 1. So that means that C times 1 equals 50. So C is equal to 50. So from this initial condition, I found out what C is. It's 50. And now I'm going to be able to solve for K with the next initial condition. When T is 75, so K times 75, we get 30 for our output for A. Okay, so now we're just going to go ahead and solve for the K value. So the first thing is we're going to divide by 50 on both sides. So that turns into a 1 right there. And 30 over 50, if you use your calculator, you get 0.6. And now if we want to undo the E part, we're going to take the natural log of both sides. And what that does is it allows us to cancel out the exponential function, because there's this property that says if you have the natural log of a number raised to a power, you can move the exponent power out to the front as a multiple. Remember that one from Algebra 2? Well, we're going to use that here. We're going to move this power out front, and we get k times 75, or 75k, times the natural log of e. And the natural log of e, if you remember, is just 1. So we get 75k. That's the whole point of taking the natural log of both sides. It cancels out that e to the power of something. Now we're going to get k by itself by dividing by 75, and we get our number for k. K is natural log of 0.6 over 75, whatever that number is. And it's going to be negative, by the way, and I anticipated this because k has to be negative since it's a decay rate. Okay, so natural log of 0.6 divided by 75, check it out, negative number. Okay, but I'm going to leave it as natural log of 0.6 over 75. I hope you don't mind. It's just easier to write than trying to memorize some stupid decimal value. So k is the natural log of 0.6 over 75 times t. And I just figured out k, so that's also this k right here. So I'm going to erase that k and replace it with natural log of 0.6 over 75. So now I've got my differential equation completed, and also my not general solution anymore. It's a particular solution for this situation. The next question says, what mass remains at t equals 100 days? So guess what we do for that? We just plug it in, okay? So let's plug in 100 for this one. So here we go, ready? So for part C, A is going to be equal to 50 e to the natural log of 0.6 over 75, and then times 100. Okay, we plug it in our calculator. We're going to have to probably round it. I bet it'll be a decimal number. And let's think about what this is going to be for units. Well, it's mass, right? And then the mass is in terms of grams. So it's going to be some amount of grams. Let's see how many it's going to be. So use our calculator, natural log of 0.6 divided by 75, and then times 100. Okay, that's that. Oh, wait. I don't need that. I need the whole thing, don't I? 50, there we go, times e to the power of, then I'll put in the rest of it, natural log of 0.6 divided by 75 times 100. There we go. That's the one I want. And so I get 25.303 grams. There's my answer for part C. And now for part D, it says, at what time was the initial mass reduced by 20%? Well, if it's reduced by 20%, so it started at 100%, it gets reduced by 20%, that means it's going to be left at 80%, okay? So for part D, here's how it starts off. Well, our initial amount was 50 grams. So 80% of 50 grams is 40. So that means that 40 is our A amount. And that's going to happen after some amount of time, T. So we're going to use our solving technique and our calculators to find out what T is going to be. Okay, so first things first, we divide both sides by 50 to get rid of that coefficient out in front of the exponential function. 50 over 50 is 1. 40 over 50 is 0.8 or 0.8. Now to get rid of the E, we take the natural log of both sides. And that just cancels out the E part, doesn't it? So what we're left with is just a natural log of 0.6 over 75 times t. So this is just like a number times t. So what I'm going to do is divide by that number to get rid of it, right? So yeah, let's just go ahead and divide this part out. So divided by the natural log of 0.6 over 75 on both sides. And that turns into a 1. So that's going to be what our t value is going to be equal to right there. And let's approximate that using our calculator. And then it's going to be in terms of, what time? So the time unit is days, I believe. Yeah, days. Because it says 75 days. Okay, so let's type it into our calculator and round it to 3 decimal places. Our units are days. So we've got natural log of 0.8 divided by parentheses natural log of 0.6 over 75 and the parentheses, so that groups the whole bottom part together, and then equals, and there's the number of days it's going to take for it to reduce by 20%, 32.762 days. There you go. So there's number 7. A, B, C, and D. All right, now let's work on number 8. All right, I'll give myself a little space here. There we go. Probably enough. A rabbit population with an initial size of 500 rabbits grows at a rate proportional to its size. So the rate is proportional to the size. So that means that the population of the rabbits, the rate at which the population grows, is going to be proportional to its size. So in other words, it's going to be equal to K times P, the size of the rabbit population. So this is another exponential model. And you know what? This phrasing is identical or synonymous, I should say, with an exponential relationship. So for part A, we already have, our differential equation completed. Not completed, I should say. We're going to replace the K in there, but we've got it we know the template. We know what it's going to look like. For part B, solve the differential equation to write the population of rabbits as a function of time if there were 1,200 rabbits at time t equals 10 days. So that gives us another, it gives us actually two initial conditions at this point. The rabbit population with the initial size of 500, that means that at time t equals 0, there were 500 rabbits. And then, 10 days later, so at time t equals 10, there were 1,200 rabbits. So we're going to use these two initial conditions to solve the exponential equation that we get. So what does the exponential equation look like for part B to solve the differential equation? Just like before, it's going to look like this. So you're going to have the population P is equal to some constant times e to the kt. And since this is like population growth for the rabbits, I know that k value is going to be positive. So it's just something to like anticipate in the future when I solve for k. I know to look for a positive number. If I get something negative, I probably did something wrong somewhere along the way. So I'm going to use the template in part B and these two initial conditions to solve. I'm going to start with using 0 and 500. So 500 is going to be the population of the rabbits when there's been no time passing. So 0 for time. So if we, solve this out, k times 0 is 0. E to the 0 power is 1. So C is going to be equal to 500. Excuse me. All right, now we got to solve for k, so we're going to use the other initial condition. And we know that 200 is going to be the population when the time is after 10 days. So e to the k times 10. All right, so we divide both sides by 500. So that part goes away, becomes a 1. 200 over 500, 2/5 is 0.4. So now we take the natural log of both sides to get rid of that e power, then divide by 10. So k is equal to natural log of 0.4 over 10. All right. Oh, wait, why did I put 200? That's 1,200, darn it. I just looked at it. Sorry about that. Made a little mistake on there. So 1,200 is equal to 500 times e to the k times 10. I think I caught myself there. So let's see. Divide by 500 on both sides again. So 500 over 500 is 1. 1,200 over 500 turns into 2.4. There we go. That's better. And then take the natural log of both sides. Divide by 10. Okay, so there's our k value. And that kind of wraps up the rest of this. The differential equation is going to be natural log of 2.4 over 10. And then the exponential expression that I get for the solution, the particular solution, is natural log of 2.4 over 10 times t. And just to verify, this should be a positive number. Let's check. So we have natural log 2.4. Oops, right as it turns off. Natural log 2.4 divided by 10. Yeah, check it out. Positive number, just like we anticipated. Okay, so we've got our model, and we've also got our differential equation. So now let's answer some other questions. It says in part C, how many rabbits will there be at t equals 50 days? Well, this just sounds like we just need to plug it in. So part C, plug the 50 into this equation. So P is equal to 500 e to the natural log of 2.4 over 10 times t, which is going to be 50 in this case. Okay, so then we approximate this to 3 decimal places. And there's going to be rabbits. So maybe, let me think, how many rabbits will there be at t equals 50 days? Let's round down to the nearest rabbit, okay? So we're just going to round down in this case just because, we want rabbits. And I don't think that it'd be prudent to talk about like, 0.28 of a rabbit or something like that. That'd be kind of weird. So let's just stick to the lowest possible rabbit. So 500, and then e to the power of, oh, darn it. E to the power of, there we go. Natural log of 2.4 divided by 10, then times 50. Enter, and man, that's a lot of rabbits after 50 days. 39,813. Okay. Good Lord. Okay. Part D. When was the rabbit population 900? So that was when we set the population 900, P equal to population P equal to 900. So 900 is equal to 500 e to the natural log of 2.4 over 10, and then times 50, or times t, I'm sorry, we're trying to solve for t. Okay, so what we do is we divide both sides by 500 first. 500 over 500 is 1. 900 over 500 is 1.8. Take the natural log of both sides. E cancels out, so we get just that stuff. Natural log of 2.4 over 10 times t. And then, if you're multiplying t by this number, we divide it. So that's going to turn into the following. It's going to be t is equal to whatever this is, natural log of 1.8 over parentheses, natural log of 2.4 divided by 10. And then, we can round that off to 3 decimal places. And this is going to be in terms of days for our units. So let's see what we get from our calculator. So natural log 1.8 divided by parentheses, natural log of 2.4 over 10. Enter. There we go. So it's going to be about 6.714 days. All right, round to 3 decimal places, and we're good to go. All right, so there we go. We got parts A, B, and C, and D done on number 8. Finished up number 7. I think this is a good place to stop this one. Then we'll do a video for 9. Yeah, maybe we'll do 2 more videos. We'll do one on just 9, but it'll be short and sweet. And then we'll do one on numbers 10 and 11. Okay, I hope you enjoyed this video. I hope it helped you out. If you didn't, just go talk to your math teacher, get some help from them. And I'm Mr. Cook. I'll be available in the mornings if you need some help or after school. All right, thanks for watching the video. See you in the next one. Bye-bye.